have 4.9 and 4.1 through 5.1 through 5.4 to 5.5. So 4.9, 5.1 through 5.5. These are the last 6 sections we have to go through. Okay, 4.9 is all about antiderivatives. Okay, what are we trying to do? We're trying to undo the differentiation process. So in other words, follow my explanation. What function do I differentiate to get 1?
X.
Excellent. However, it's x plus any constant, right? Because when I differentiate x, I get 1, and when I differentiate the constant, I get 0. Good, perfect. So this can be any real number. Perfect. Now, what if I want to determine the function whose derivative is x? What do you think will fit in here? Don't be afraid to be wrong. It's okay. We're learning this.
What's your question again?
Yeah, which function should I have here to differentiate and get x?
F of x.
True. But as we had here, x prime is 1. What prime is x? Well, we increase the power by 1 and we divide by that number. Of course, plus a constant c. So the point I'm making here is that this is a family of functions. This is not just a unique answer, right? So x plus c is a family of functions. So same thing here. So how do I differentiate x squared? Bring down 2, simplify with the 2, and I get x. Differentiate c, get 0. So we can continue forever, but I think you're getting the pattern. Which function prime, or what would be the rule here is, if I want to get x to the nth power, all I have to do is increase the power by 1, divide by that number, and of course, if I want the entire family of functions. So this is called this with a c, even that, the same thing. X plus c is also called the most general antiderivative of 1. So the reverse operation, the most general antiderivative of 1 is x plus c. So here's the power rule, basically, right? So if I want to determine, if, for example, if we have the function f of x equals x to the third, and we're asked to find the most general antiderivative, let me put lowercase f, and I'll explain why the notation should be either f of x or f prime. So the most general antiderivative will be, according to the rule, increase the power by 1, divide by that power, plus a constant c. What is this? The most general antiderivative of x cubed. It's a family of functions. If you differentiate this, you're going to get x to the third. And now about the notation. And then we'll look some at examples. So I could be given f prime, and I could be asked to find the function whose derivative is this. The other alternative is I am given f of x, but then I will have to use this uppercase notation to find the antiderivative. you can say, what's a big deal here? Why can't you just use f of x uppercase here both? Because of the fundamental theorem of calculus. Okay, so if we're given a derivative, we can find the function. If it's f, we have f. If it's g prime, then we use g, of course. But what if I'm given the second derivative? Can I determine the function? Yes. But first I have to determine the first derivative, and then from the first derivative, I will find the function. It can be the most general antiderivative, or it can be just a unique situation if we are given some other conditions. Okay, so allow me to share my screen. I want to go to the book. I'll show you in a second. Where is my share screen button? I got it. Okay. It doesn't matter, but it's the same book, but I'll stick with 191. It's the same thing. Okay, so we go to the last section of chapter 4, which is 4.9. If my device will cooperate. Okay, I'm waiting. Good. Okay. Chapter 4, 4.9, Antiderivatives. And I'm sure you have on the tip of your tongues the question, why are we looking at antiderivatives? And that is a very good question, and I'll explain in a minute after we practice a little bit. Okay, so I'll start with, let's say, number 9. Number 9, we're asked to find the most general antiderivative of the function. Okay, so in number 9, we have the function f of x equals x, 12x plus 8. Very simple situation. Of course, I will distribute. This is 12x squared plus 8x. Since I'm asked to find the most general antiderivative, since I'm given this notation, I will use this notation for the most general antiderivative. And I know it's 12. The constant stays in front, like for limits, like for derivatives, for everything, right? As long as it's a product. And then this becomes x to the third over 3 plus 8. Of course, this becomes x squared over 2. And then plus a constant c, the most general antiderivative. I would have to clean it up. I get 4x cubed plus 4x squared plus a constant c. Can I check? Of course. F prime of x must be f of x. If it isn't, then this is wrong. So let's check. 12 and subtract 1 from the power. 8x, subtract 1 from the power. C prime is 0. Okay. And we can choose anything else from here, of course. But I just want to jump to an example because I want to explain why we're doing this. And then we'll come back to as many problems as you want. Okay. So here's an application in which a particle is moving with a given data. Find the position of the particle. So the position of the particle means the distance formula. Like, so we are given, let's say, in 65, v of t equals 2 cosine t plus 4 sine t, and we are told that s of 0 is 3. So I chose this example mainly to explain why antiderivative, and what it means. What does it mean? Why will I ever look back? So notice that this is not the distance formula. This is basically v of t, which is the derivative of the distance formula. But I don't have it. We are asked to find s of t. So we're, so far till this section, we were used to get the function and find its derivative, to look at the rate of change, to look at who knows what, graphing, etc., and all sorts of applications, max, min, who knows. But no, this time we're going backwards. We are given the velocity formula. Somehow we have the velocity function of t for this particle, and we're asked to find the distance formula. So that's one reason why we're looking at anti-differentiation. Undo the process of differentiation. That's what it means. So undo the process of differentiation to get the previous function, the first function, which is the distance function. Okay, so s of t obviously is, what function prime is this? Can anyone tell us what function prime is this? 2 cosine t. What should I write here?
2 sine t.
Yes, excellent. 2 sine t, because 2 sine t prime is 2 cosine t. Perfect. Now, what function prime is this? So please, I'm begging you to pay attention. I see you are. So this is very important. And stop me. Yes?
4 cosine t.
Very good. And of course, we have to add the constant. This is a family of functions. However, this is called an initial condition. Can anyone tell us why this is given to us? What do you think? It's okay if you're wrong.
So you can solve C.
Exactly. Excellent. So now this will be a unique function. Once I find C, right now it's a family of functions. Millions and billions of functions have the same derivative. But once I plug in this condition, that will give us a unique function that satisfies two conditions. This, in other words, its derivative is this, and also s of 0 is 3. So in order to, we know what that means, s of 0 is 3, means that 3 is this, the function, when t is 0. Sine t is 0, but cosine t is not 0. Cosine t is 1. So -4 plus the constant c, which means when I move this to the other side, the constant is 7. And now this is a unique situation. S of t, 2 sine t minus 4 cosine t plus 7. So this is one application of anti-differentiation, not the only one. You'll see the rest in the next chapter. Okay, so now let's see if you'd like to pick. If you don't want to pick, I will. We are given the velocity. Here we are given the second derivative of the distance. Here we're given the first derivative. We're asked to find the distance. And all the other examples. Anything you like from here? I think we should pick at least another one or two and move on. You choose.
The second derivative one, please.
Yes. So like something like this you want?
Yeah, that looks good.
Or the third? Okay, we want to look at 46 then?
Yeah.
Okay, 46 it is. Very good. 46. Where are you, 46? Okay, the second derivative. As you know, I'm looking through a cage. One of my students said, Professor, take down that cage and get some fresh air. Last semester. I thought it was hilarious. F of 1 equals 0 and f prime of 1 equals 8. Okay, did I copy the correct problem? Okay, so my cage is in front of me and I can't see very well over there. Okay, good, perfect. Okay, so for this problem, we are asked to find the function. Why not uppercase F? Because I have f prime or f double prime, right? I'm looking for this. If this were f of x, I would be looking for uppercase f of x, but that's not the case here. Okay, I cannot jump from the second derivative to the function. I have to continue with the first derivative first, or find the first derivative first. As we know, 8 increase the power, x to the fourth over 4 plus, which function prime is 5? Well, that is 5x plus a constant c. I'm going to copy it here again because it's, as you know, I always run out of room. So this is 2x to the fourth plus 5x plus a constant c. I notice that we have two initial conditions, and one of them is specific for f prime. It says f prime of 1 is 8, which means I can solve for c. F prime of 1 is 8. 8 equals 2 plus 5 plus c. 7 subtracted from 8, c equals 1. I have the unique derivative, which is 2x to the fourth plus 5x plus 1. I have one more step to find the function. And I will continue with f of x equals 2x to the fifth over 5 plus 5x squared over 2 plus which function prime is 1, which is x, plus a constant d, not to be confused with c. Or you use c1 here and use c2 here, whatever, but make sure you use different letters. c1 and c2 are fine. Okay, and this condition, f of 1 is 0, which means 0 equals f of 1. So 2 fifths plus 5 halves plus 1 plus d, of course. Okay, so then the least common denominator is 10. And everything will be negative. So this is 2, and this is 5, and this is 10. 4 plus 25, 29, 39. And this is it. So we determine the function, the unique function, the only one, 2 fifths x to the fifth plus 5 halves x squared plus x minus 39 divided by 10. It's the only function that fulfills the given conditions, all of them.